Okay. So can you see my screen? Yes, please respond. Anybody?
Yes, sir.
Yes, sir.
Okay. So we were discussing about load carrying capacity of the pile, right? So in our previous class, we have already seen the static approach. Okay, so there are two types of two types of calculations. Like to calculate the load carrying capacity, one we can use either a static approach or one more is dynamic approach. Okay, so the dynamic approach I will take some other time. Okay, so today we'll discuss. I already discussed about this static approach, but I will just brush up your mind and so that we can solve some problems based on this static approach. Okay. So what is the static approach? See, this is the pile. Pile, and this is the surrounding soil. So once you install this pile, whatever the load is coming on the pile, it will be shared among uh, shaft resistance and a tip resistance or base resistance. Okay, so this shaft resistance is called as QS, and the base resistance is called QB. Okay, so this is the base resistance and this is the shaft resistance. Okay, so how to calculate that base resistance? This base resistance is nothing but, okay, so the unit base resistance into the cross sectional area. And what is the shaft resistance? It is the unit shaft resistance into surface area. Okay, so this is the cross sectional area, that is the base area, and this is the surface area. Okay, so this is see, summation I going from 1 to n means, suppose if you have a different layers of soil, then you have to calculate the shaft resistance for different soil layers. Suppose here I have a sand, and here if I have a clay, and again sand. Okay, so then I have to add up all the shaft resistance. So that's why I'm putting the summation I from 1 to n. Okay. So first we will see what is QBU, how to calculate QBU. Okay, so if you remember our shallow foundation bearing capacity formula, so it is simply cohesion into NC plus gamma dF into NQ, or QNQ also you can call. Okay, so this term is nothing but Q. Okay, so QNQ plus 0.5 gamma B N gamma. Okay, so this is the for shallow foundations. Okay, so but in deep foundation, what will happen? It is almost it is almost same like your shallow foundation. Okay, but the failure surface is restricted to only for a smaller depth. Okay, because your width of the pile is very small. Okay, so this width of pile may be some 500 mm or maybe 600 mm. At the max, it may be 1 meter. 1 meter is too big at all. Okay, so this 500 to 600 is typically used in practice. Okay, so but whereas your stiff footing width will be like 1.5 meter to maybe around 2 meter. Okay, so the width will be higher here. Okay, that's why the failure surface also very small here. Okay, so here we usually will get this general shear case, and here we will get a punching shear case. Okay, so usually this very small this area like your cross section area of the pile is very small, no? So we will get something kind of a punching shear failure. No? So that's why a little the formula broadly, the formula is it should look like your a shallow foundation. Okay, so if you see now I'm discussing in granular soil. Okay, so whatever static approach I'm discussing, that is applicable only for the granular soil. Okay, so once granular soil means here C will be 0. Okay, so first term, that's why first term will not be there here. Okay, so if you recall, that is CNC plus CNC plus QNQ plus 0.5 gamma B N gamma. Okay, so since C is 0, this term will be 0. So QNQ, Q is nothing but your sigma bar. I'm representing here with sigma bar into NQ plus 0.5 gamma D N gamma. Okay, so almost same like your shallow foundation bearing capacity formula for the to calculate the base resistance. Okay, so this is the formula to calculate the base resistance. Okay, so what are the parameters here? Sigma bar is nothing but it is the effective overburden pressure at the pile tip. and what is the NQ and N gamma are the bearing capacity factors. Okay, so this whatever this N gamma is there, no, this N gamma I have to take it from IS 6403. So I have to go back to IS 6403 and can pick up this N gamma. And this NQ value is there, no, this NQ value I have to take it from IS 2911. Okay, in 2911 there is a chart where for different phi value, we have N gamma value. Okay, so later on I will show the IS 2911 also where to see this chart. Anyway, IS 6403 already explained in the table number 1 they given for different phi value NC, NQ, N gamma they given. Okay, so for N gamma value you have to refer to 6403, and for NQ value you have to refer to 2911. Okay, but see, you need not to refer because this term I'm going to neglect it. This term, whatever this second term is, this term I am going to neglect because the depth, your diameter of pile is almost very negligible as compared to your depth of foundation. Okay, so this depth will be in terms of 15 meter up to 20 meter depth will be there, but whereas your diameter will be only 0.5 meter, very small compared to this term. Okay, so many times what they will do, they will neglect this term. But IS 2911, what they will in 2911 they won't neglect this term. Okay, so they will include it. Even though if I neglect also, I will be on the conservative side. See, this much capacity I am not including in my calculation. That means I am on the safer side, even though if I neglect it. Okay, so but 2911, what they will tell, they will in that this term also they will ask you to consider this term also. But anyway, for time being, we will neglect this term. Okay, once if exclusively if they mention that solve the problem by IS 2911, then you can consider. Even though if you neglect also, it's not going to differ much in your final answers, because that the contribution of this term will be very small. This term contribution will be very small. Okay. Then that's what I have written here. 0.5 gamma D N gamma is negligible compared to your sigma bar into NQ, hence it is neglected. So finally your base resistance is what? Base resistance is sigma bar into NQ into your cross-sectional area. Okay, that is base cross-section area of your base of the pile. So this NQ is the function of a phi value. Okay, so this NQ I will get it from 2911. Okay, IS 2911. Okay, so see, sometimes what they will do, they will limit the whatever value you will get. No, so some upper limit value they will fix. Okay, so like that. See, they usually will tell that around this QBU is there. No, this QBU are not capital QBU. This small QBU. Okay, this term is not small QBU. Okay, this whatever this unit base resistance will be there. No, this unit base resistance they will put the upper limit value. Okay, so that means how much they are putting? 11,000 kilopascal. Okay, so if at all if you are getting more than 11,000 kilopascal, then restrict that value to 11,000 kilopascal. So usually these kinds of cap value they will put, because always there will be some uncertainty will be there in the calculation of these all properties. Okay, so that's why this kind of limiting value they will put. So 11,000 kPa is the limiting value for the base resistance, that is unit base resistance. Then once we see this NQ value, anyway they will give given by different authors they will give, but 2911 curve will refer to 2911 curve. The different phi value, here is the NQ value. Now once the base resistance is over, now we will see how to calculate the shaft resistance. This is the QS. Shaft resistance is nothing but summation I from 1 to n your unit shaft resistance into surface area. Okay, so what is this unit shaft resistance? Unit shaft resistance is nothing but your earth pressure coefficient times your vertical overburden pressure into tan delta into your surface area. Okay, so this Ki is the this is called as coefficient of earth pressure. Usually it will be 1 to this Ki value will vary between 1 to 2 for driven pile and 1 to 1.5 for board piles. So you can assume accordingly. If in the problem itself they mention the k value, then you take that k value. If they not mention anything about the k value, then you take, if it is a driven pile, if the pile is driven pile, then take between 1 and 2, and if it is a board pile, you can take between 1 and 1.5. And this what is a sigma AVI? Sigma AVI is nothing but average effective overburden pressure for each layer. Okay, so whatever suppose this in this problem I have only one layer. Okay, so average means here it will be 0 and here it will be some quantity. So 0 plus some quantity divided by 2 will be my average cohesion value, or my average what do you call this overburden pressure. So always at the middle I should take. So this is my sigma AVI, that is the average overburden pressure. And what is this delta? This delta is the angle of wall friction. That is the frictional coefficient between soil and your pile. That is the delta value. Okay. So usually what will happen, this delta value, some for board piles, you can take your phi value itself as a delta value. If it is a driven pile, then you can reduce that delta value. Okay, so that means around 2/3 of phi value you can take. Okay, so in the problem itself they mention the delta value, then you take that value. Otherwise, if they not mention that delta value, then you should remember this 2/3 of a phi value for driven pile, and is equal to phi value for board piles. Okay, but in IS 291, if you refer IS 2911, then what they will suggest, no, this delta almost you take it as a phi value, according to IS 2911. But some researchers, what they will tell, they will ask you to reduce delta value by 2/3 times in the driven pile, because in the driven pile what will happen, there will not be there will be some disturbance will be there between your pile and soil, and also there will not be much clear cut this bonding will not be there. Okay, so that's why they are reducing some phi value in case of driven pile. But whereas in board pile, the disturbance will be less and there will be very good bonding between pile and soil. Okay, so that's why you can take phi value itself as a angle of wall friction. And even also here also they will mention you about some cap value. Okay, so that means your shaft resistance, that is QSI, total QSI should not be greater than around 110 kPa. 110 kilo Pascal. Okay, so this is the cap value, that is limiting value. Okay, if while calculating, if you whenever you are solving the problem, if you get the your surface, your skin resistance or unit skin resistance more than 110 kPa, then you should restrict to 110 kPa. Okay, so usually see this some people will follow this limiting value and some people will not follow, because they will tell that, okay, so whatever the shaft resistance from the pile, I will full value they will take. Okay, suppose even though if they are getting more than 110 kPa, some researchers they will suggest that also. Okay, so you take whatever value you will get. Okay, so don't restrict your shaft resistance to 110 kPa. Okay, so both way, if you refer different textbooks, they will solve these problems in different way. Okay, so there is no unique or a single method. Okay, so this is based on research. Some people will put some capping value. If you refer some other author, they will give this number will be some higher value. Okay, it all depends on these to whom you are referring. Okay, so but we will stick to IS 2911. IS 2911, what they will tell, accordingly we will solve it. Okay, so this delta value and k value I told now. So according to Brooms, they will give for different this pile material, delta value they will give, and and also for k value also they are giving here. Okay, so but if you refer IS 2911, recommends that delta is equal to phi value. That's what I told in the previous slide. So they won't reduce it by 2/3 times for the what do you call this driven pile. They will take Sorry, I got some disturbance. Okay. Yeah. And one more thing is this critical depth concept. Okay, so some researchers, what they told is, see, whatever this overburden pressure is there, no, this overburden pressure will not increase along the depth. Okay, so what they are telling, it will increase only up to certain depth, then it will become constant. So this depth is called critical depth. Okay, so it is usually it will be 15 times the diameter of the pile if your phi value is less than 30 degree. Okay, so or you can take this critical depth as 20 times d also, that is the diameter of the pile. This d is nothing but diameter of pile. Okay, so this is the critical depth concept. Okay, so even see, if you refer some textbook, they won't consider this critical depth. Okay, so what they will tell, they will take full this variation of your overburden pressure. That means this linear variation, whatever linear variation will be there, no? So total this linear variation they will take. But IS 2911, they will tell, what they will tell, they will tell you, like you consider critical depth. Up to critical depth, you take your overburden pressure with linearly increasing. Then from that depth, you curtail this. You curtail and it will become a straight line. Okay. So suppose here some 20 kilonewton per meter square, if you are getting, then the same will continue for the rest of the depth. Okay. Okay. So this is the final formula. Okay. So this is the base resistance, and this is the shaft resistance. Okay, so this, whatever till now we discussed, this is applicable only in the granular soil. Okay, so till now whatever soil we considered, that is only granular soil. But if you refer IS 291, this is the formula. Okay, so this formula is almost similar to this formula. Okay, if you compare these two, they are nothing but same. Okay, only extra term here is this term. So what I told now in the beginning. Okay, so this term usually we will neglect it because the contribution of this term will be very small as compared to the first term. Okay, so this contribution will be neglected in the normal calculation. But IS 291, they will consider that term also. And one more thing, see, this ultimate load is there. This your base resistance, shaft resistance minus the weight of the pile. You have to consider the weight of pile. Some people, they will consider even this weight of pile also, because see, whatever the suppose here your this is your pile. Suppose this is your pile and this is my so this is my ground level. This is my ground level. So see, this whatever soil is there, this has to resist even the weight of the pile along with the whatever Q value is coming. Along with the Q value, it has to resist the self weight of this pile also, no? So that's why people, what they will tell, they even in this while calculating your ultimate load carrying capacity of the pile. So the base resistance anyway, it will resist that one. So that's why it's plus, and shaft resistance also it will resist the Q value. But whereas your weight of the pile is along is in the same direction as your Q value, no? So that's why I have to deduct the weight of the pile. If you refer some textbooks, even they will tell you that you have to deduct the weight of the pile. But in our calculation, I will neglect this because compared to this resistance, whatever resistance you will get from the base resistance and shaft resistance, the weight of the pile is very, very negligible. Okay, so I can neglect that weight of the pile. But if you go to the offshore structures, in the offshore structure, what will happen? See, your pile will be kilometers together because the sea depth will be very, very high, no? So the depth of a sea. Okay, so in the sea, this height will be very, it will be in kilometers together. Then what in that, for example, the depth is relatively higher in offshore structures. Okay, so in the offshore structures, you can't neglect this weight because this weight of the pile will be significant. So in the in our conventional onshore structures, we can neglect the weight of the pile, because the weight of the pile maximum it will be 20 meter. So maximum it will be 20 meter. Okay, so if we compare to this load, this 20 meter pile weight is negligible. Okay, so that's why I'm not putting the weight of the pile. But if you go to the offshore structural engineering applications, then you should the weight of the pile will be significant. Okay, so this is the IS 2911 formula. This is the tip area into PD into NQ. PD is nothing but your overburden pressure. Okay, so this sigma and PD are same. Only nomenclature is different. Okay, so in the IS 291 they are referring PD, but here in my slide I am referring it as a sigma bar. This is nothing but overburden pressure only, and NQ anyway same. So this 0.5 gamma D and gamma anyway we have neglected in our calculations. Okay, and this is your base resistance part. This is the base resistance part, and this is your shaft resistance part. So this shaft resistance part is here. You see, K into sigma bar into tan delta. Okay, so K into PDI. PDI is nothing but your sigma only. Okay, overburden pressure into tan delta into surface area. Okay. So any doubt till now? I hope we have not lost any connection, right? Because just now I got some call. Whenever I get a call, the connection will be lost. All of you can hear my voice, no? Right? We are in the right track, right? No issue. Okay. So any doubts till now? Any doubts regarding the these pile load carrying capacity in sandy type of soil? Prajwal? Are you there, Prajwal? Aishwarya?
Yes, sir.
Any doubts regarding the formula, whatever we discussed till now?
No, sir.
Okay. So this is for as far as granular soil is concerned. Okay. So now we will see these how we can calculate the load carrying capacity if you have a clay type of soil. That is your cohesive soil. So this is cohesive soil. That is clays. So Q ultimate equal to your base resistance plus shaft resistance. What is base resistance? Base resistance is your base area into undrained cohesion and into NC value, plus into this is your shaft resistance, summation I from 1 to n, alpha times your CUI into surface area. Okay, so this alpha value is this alpha value, it depends on CU value, and that is undrained cohesion. So whatever the undrained cohesion will be there, it depends on alpha value will depend on that undrained cohesion. So this chart is from 2911. Okay, so this is IS 2911. Okay, if you see on the x-axis it's undrained cohesion value, and on the y-axis the adhesion factor. Okay, that is alpha value. Okay, so depending on your depending on C value, you can take the alpha value here. Okay. Okay, so these formula, see whatever till now we discussed, this is general formula, but if you refer IS 291, they will tell you that's what I discussed here. Okay, so whatever this formula is, this formula is this same thing here. Same thing here. So this is according to IS 2911 in granular piles. In the granular piles. Okay, so these terms already we have discussed. The only thing here you have to concentrate on this K value. In the K value, so in the IS 2911 they will tell you can take from 1 to 2 for dense sand, that too in a driven piles. Okay, so if you have a driven pile, and if you have a 5 value anyway between 30 to 40, then if you have a 30 degree, then you take it 1, and if you have a 40 degree, and then you can take 2 K value. See, if nothing is mentioned, if you are not able to remember this thing, simply what you can take, the best way is just to take K is equal to 1. irrespective of any pile, whether it's a board or a driven pile. And if they mention in the problem, then it's well and good. You take k value as 1, k whatever k value is given in the problem statement. Okay, so if they in the problem statement, if they are not giving k value, then you can, if possible, you remember this thing range for your a driven pile and board pile, or simply what you can take k equal to 1. It's always the conservative value you can take. And in the IS 291, this whatever is NQ value is there. I told you NQ value. This NQ value, if you have a driven pile, then you have to refer to section 1. And if you have a board pile, then you have to refer to section 2. So for the driven pile and board pile, your NQ value will change depending on my phi value. Okay, so if you have a driven pile, then you take whatever phi value you take, and corresponding NQ value you can take here. And if you have a this board pile, then you have to refer to this curve. So this section 1, this section 1 will speak about a driven pile, and this section 2 will speak about a board pile. Okay. Anyway, this n gamma value, it is from IS 6403. If you refer IS 6403, this n gamma value you can take. Okay, so again, same IS 2911 in case of clay soil. Okay, in case of clay soil, you have to like same formula only. If you see here, our this formula and this formula, only some nomenclatures are different. Okay, so whatever nomenclature I am referring and whatever IS 2911 is referring, little bit difference will be there. But they are essentially same. Here it is nothing but NC into CP. Alpha into Ci into your surface area. This is your base area. Okay. But what I suggest is you don't bother about these formulas from whatever IS 2911 is there. No? So I would have avoided these formulas, because see, anyway in the syllabus they are not mentioned as 2911, so you stick to these formulas only. So in the final PPT, whatever I will share, I may delete these things, because these and these are essentially same only. If I put both, then you should not get confused between these nomenclatures. Only the difference is the nomenclatures. Otherwise, they are essentially same. There is no difference at all. If you consider my general method and your IS 2911 method, almost they are same only. Okay, so next see what is negative skin friction. So in the negative skin friction, what will happen? See, whenever this pile, wherever you have a fill material, what do you mean by fill material? Like recent deposits will be there, no? So whenever you have these kinds of recent deposits, what will happen when you are driving the pile? What will happen? The surrounding soil will settle more than your pile settlement. That means what will happen? This whatever this negative skin friction, it will add some drag force on this pile. So instead of resisting the force, it is in the same direction as your Q value. Okay, so that's why wherever your negative skin friction layers you will get, no, that you should deduct in the final ultimate load carrying capacity. Suppose here you see this is the fill material consolidating under its own weight. That means once if you drive a pile in a very loose soil, what will happen? The more than pile settlement, or what will happen? The soil will settle. Once the soil is settling more than your pile, it will produce some drag force on this pile. Okay, so that means instead of resisting, it is negatively it is affecting your load carrying capacity. That's why it's called as negative skin friction. So this is you see this is also negative. See how you can identify certain layers which are affecting my skin friction. If you see this arrow mark is in the same direction as your load applied, right? So that's why these are negative skin friction. But if you see this one here, this is positive skin friction because it is resisting your load, whatever load is coming from your pile, no? So I'm putting a arrow mark like this, right, in the opposite direction of your applied load. That's why this is positive skin friction, this is negative skin friction, and this is also negative skin friction. So usually this negative skin friction we will encounter in recent deposits or fill material. So in the recent soil deposit, suppose if soil is not at all undergone any consolidation settlement, or recently some soil is loosely deposited and there you are driving the pile, means you have a chance of getting negative skin friction. Okay, so what we can do to avoid that negative skin friction? Some people, what they will do, usually in the field, we will apply some bitumen layer on the soil, bitumen layer on your pile, so that whatever drag force is there, that will be nullified. So once you put a bitumen layer around this pile in the region where you can expect a negative skin friction, then in that way you can nullify the effect of your negative skin friction. You have to apply some bitumen coating. Okay, so that's what I explained in these bullet points. Okay, so you can go through these all the bullet points. Okay, so essentially what I saw, the same thing I summarized just now. Okay, so with this background we will solve some problems. Okay, so let us go to some problem section. Okay, I will take a fresh page here. So this is unit 5. So first problem we take down. Let me write anyway here. So there is a pile here. So this is the pile, and here we have a ground level. Okay. So this is 15 meter long pile. The length of the pile is 15 meter. This is 15 meter length of pipe, and the diameter of the pile is 300 mm dia. Okay, let me write 300 mm dia. 15 meter long. So this is the dense sand. Okay, so whatever this 15 meters is, is single soil layer. Okay, so this dense sand. And there is a water table here. So the water table is a depth of 2 meters from the ground level. So this is water table. This is 2 meter. This is 2 meter depth. And the unit weight of this dense sand is the, no? So this saturated unit weight is equal to 19 kilonewton per meter cube. 19 kilonewton per meter cube. Okay, and K value, so the given K value is 2. Okay, so it is a actually driven pile. Okay, so this is the driven pile. Driven pile. Okay, so phi value given 40 degree. 40 degree they given phi value. Okay, now let us see what is the formula to calculate ultimate load carrying capacity. It is QU is equal to, tell me, base altimeter plus shaft altimeter. Okay, so this base altimeter is nothing but your unit base altimeter. Small QBU into base area plus small QSU into surface area. So first, this is your Q ultimate. Okay, so first calculate this parameter. Okay, so this is Q BU is equal to small Q BU into base area. So here we will apply critical depth concept. So okay, but some people, what they will tell, they won't consider critical depth. In that case, your sigma bar should be calculated for entire depth. That is DC. So how you can calculate the critical depth? So critical depth, that is DC, is equal to 15 times the diameter, or you can take or 20 times the diameter. Okay, so if it is phi value is less than 30 degree, then you can take 15 times. So if your phi value is more than 35 degree, then usually 20 times. Okay, so here phi value is 40 degree, so I will take 20 times D. So critical depth is equal to 20 into your diameter of the pile is 0.3. So around 6 meter. So this is 6 meter is my critical depth. That means up to 6 meter the variation will be there. After 6 meter the your this thing overburden pressure will be constant. Okay. So this depth is called what? Critical depth. That is DC. Okay, so what is the formula here? QBU is nothing but your sigma bar into NQ into AB. Okay, so what is NQ? How we can get NQ value? So NQ value, suppose for it depends on, NQ value depends on what? NQ value is depends on phi value. It depends on phi value, angle of internal friction. For what is the angle of internal friction? They given in the problem around 40 degree. Okay, so for that 40 degree, let us go to the IS 2911. Okay, so okay, this is the driven. See, IS 291 part 1. Okay, section 1 I am referring here. The opening. Can you see there? IS 2911 part 1 section 1. Okay, revised in 2010. So this section 1 it deals with driven cast in situ concrete pile. Driven cast in situ concrete piles. So if you in this one, if you go to see, anyway, these codes I will upload in the Google Classroom. You can download from there. Now I will directly go to here. Okay, so this annexure B I will go. This, and in annexure B, their load carrying capacity from static analysis you will see. So this is the formula. That's what I shown in my PPT also. Same formula: AP into half gamma D n gamma PD into NQ. Summation I going from 1 to n. All of you can see this, no? Should I increase this font size here? Is it okay now? Okay. So this is the formula. So pile in granular soil. Here, if you go to this figure number 1, in the figure number 1, the bearing capacity factor NQ for driven piles. What is the phi value we have? We have phi value of 40 degree, right? For this 40 degree, this NQ value, this is 100, so 100, 200, 300, 400, 500. Okay, this is 200. This is 250. Okay, so sorry, not 250, 150. This may be around 150. This is 200, no? So this you can take it as 130. So NQ value you can take it as 130 degree. Go back here. So NQ is equal to 130. How I got this 130? From IS 2911, IS 2911, part 1, section 1. Okay. What is the graph number? It is the figure number 1. So this is figure 1. So this is my NQ. Now put here everything in this formula. I will get the QBU. Okay, so QBU is equal to what is my sigma bar? Sigma bar, how much I got? 6 meter. No, this is in that also 6 into. So first, let me calculate here. This is up to 2 meter. No, so this is up to 2 meter. So this value will be this soil will be in dry condition and this soil will be under saturated condition. Okay, so 2 into your dry density. Okay, so dry density I will consider it as a 19. Okay, so my dry density as the saturated density I will consider same only. Okay, so 19 into 2. Around 38 kilonewton per meter square. Okay, then at this level, this is up to 2 meter. Then up to this critical depth is I got 6 meter. No, so remaining is 4 meter. So this 4 meter at this level. This is at 4 meter. At 4 meter, again I have to calculate my overburden pressure. Okay, so 38 plus 4 into my unit weight. Unit weight is 19. So I think I will get around 74 kilonewton per meter square. 74 here, 74, and the same 74 will you will carry on up to here, 74 kilonewton per meter square. Okay. So all of you are following or not? Whatever I am writing here. Any difficulty? Is there any difficulty? Shall I continue it? Are you following or not?
Yes, sir.
Okay. So now let us have this QBU. QBU is equal to how much we got? 74. Not 74 was my overburden pressure. Okay, so 74 into NQ. NQ how much? 130. 130. 74 into 130. That into base area. So that is pi by 4 into diameter. What is the diameter of this pile? 300. That is 0.3 meter. Pi by 4 d square. How much you are getting? QBU. Calculate. How much?
$679.9.
Yeah, 679.9, almost 680 kilonewton per. Okay, only kilonewton. Okay, it's a load. No QB. Anyway, I'm multiplying with the area here. It's a kilonewton. This is the base resistance. Now we have to calculate the shaft resistance. Okay. So what is the shaft resistance? QSU. So shaft resistance is equal to small QSU into surface area. So what is this small QSU? Sigma average into K into tan delta into my surface area. Okay. So first, see the surface. This whatever skin friction is there, no? This skin friction will be different in this dry area, and skin friction will be different in your because your sigma, your overburden pressure will be different, no? So your overburden pressure is different in this dry area and in this wet area. Okay, so that's why I will calculate separately this surface, this skin friction, and this skin friction I will calculate. So,
Sir, repeat the calculation of overburden area, sir.
Overburden pressure. Huh? Okay, see.
Yes, sir.
Yeah. Shall I erase this and I will recalculate? Okay.
Okay, sir.
Okay. I will draw with the different color so that you can differentiate. Okay. So first, up to 2 meters the soil is dry. Okay, so for that I will calculate now. So up to 2 meters first. So this is to 2 meters. So what is the overburden pressure here? 2 into 19. 2 into 19. How much you are getting? How much? Around 38,
38.
right? Yeah, 38 kilonewton per meter square. kilonewton per meter square. Okay. Now this is up to 2 meter over. Now see your critical depth is up to 6 meter, no? So up to 4 meter I have this is 2 meter depth, and this is I will take this here up to here somewhere here. So this is 6 meter. Total 6. From here to here it is 6, but from here to here it is how much? 4 meter. So here this thing 2 into 19 plus 4 into 19. But here see here the soil is under submerged condition, right? So I have to take 19 minus your unit weight of water. 19 minus 10 I will take. Okay. How much you see? Now you are, how much you are getting?
74, sir.
74. Huh?
Yes, sir.
So 74. Okay. So this is my 74. Okay. So from here it will remain same. Okay. So this is also my 74 kilonewton per meter square. Understood? This one.
Below 74 it is dense sand, so it remains same, sir.
Yeah. Because I have to see that whatever the critical depth I told, no, up to critical depth the variation will be the linearly it will increase. Once you reach that critical depth, then whatever the stress is here, no, stress will remain same here.
Okay, sir.
The stress will be same. Okay, so that is called as critical depth concept. If you remember in my PPT, I have put one. Just I will clarify what is that critical depth mean. So let us go back to my PPT here. Okay. See why this critical depth concept is coming, because of soil arching. Okay, so there is a phenomena called soil arching. Wait a minute. Some problem. Okay. See why this stress remains same after critical depth. After critical depth, the stress remains same. So that phenomena is called as a soil arching. Soil arching. So this soil arching is nothing but it is just like your arches will be there. No, see here. See this arch, over this arch you have a large weight. Sorry. Here this arch has to carry this much load. No. Can you imagine only a small arch whether it can carry this much load? It can't carry, no. If because of arching effect, what will happen? Whatever this over this load is there, no, this load will be distributed to here sideward. This load will be distributed here. So that's why these arches are very efficient in order to take the whatever load present over these arches. So this whatever load is present over this arch is, this load is not taken by only this whatever stone present here. This is called as crown, something called that crown. What do you call that? Stone crown. Some crown they will call this. One rock will be there here at the junction of your arch. Okay. So this whatever this load is, this load will be distributed to sidewards. Okay, so this phenomena is called as arching phenomena. Okay, the same phenomena also will occur in soils also. Okay, so that's why this whatever increase in stress is there, this increase in stress it will keep on increase. Okay, so it will keep on increase up to certain depth, then it will become constant. So that depth is called as critical depth. So see, again, this is a very still debated problem, because some researchers, what they will tell, in the field you won't observe this kind of arching, they will tell. Okay, so that's why if you refer some textbooks, no, they will take a full linear variation, they will take. They won't curtail here. Okay, so if you take a linear variation, then what will happen? You see in this my problem, this thing will simply it will increase the stress here. Instead of 74, I should have got 74 plus what is the remaining depth? Remaining depth is around 6 plus 4, 10, 9 meter. Okay, so 9, yeah, 9 into 10, that is 10, 19 minus 10, that is 9. 9 nines are 84. Okay, so 74 plus 84 would have got my this effective stress here, if I not consider my critical depth concept here. If I not consider critical depth, how much I would have got here? 74 plus around 84. That much stress I will get. Since I'm this IS 2911, they are asking, they will tell you to consider the critical depth. That's why I'm solving according to IS 2911. Even if you not consider, that is also fine. Because some textbook they will allow, some researchers they will tell this critical depth concept will not be available for all type of soils in the field. Okay, so here what I'm doing, basically I am playing safely here. So I am underestimating my pile capacity here. See, if I got here around suppose 120 kilonewton per meter square, then my load carrying capacity of the pile would have increased. So I will see what I will do today. I will solve by employing the critical depth concept. The same problem I will take and I will solve without considering the critical depth concept in tomorrow's class. Okay, so that you can see the difference between both. Okay, so am I able to convey the message? If anybody is having doubt, please let me know. Shall I proceed?
Yes, sir.
Okay. Okay. So first I will calculate your shaft resistance for the first 2 meter. Okay, because for the first 2 meter the shaft resistance will be different. Okay, so here in this region, from here to here, from here to here shaft resistance is different. From here to here shaft resistance is different, and from here to here shaft resistance is different. Okay, so 3 shaft resistance I will get here. So let us, because why shaft resistance is different here? Because here it is average shaft resistance I should take, no? Sorry, average effective overburden pressure. So here it is a 0, and here I am getting around 38. So average is 0 plus 38 by 2. And here again it is varying from 38 to, it will vary up to 74. Okay, then the uniform here, from here to here it is uniform. Since my sigma AV is varying, that's why my shaft resistance also will vary. Okay, so first I will calculate for the first 2 meter. Okay, that is in dry portion. So QSU1 I will write. Okay, that is a unit shaft resistance for the first 2 meter. So I will, from 0 to 2 meter it is, from 0 to 2 meter. So what is the formula? Your sigma average. So I have to consider your average shaft resistance. Okay, so that is sorry average overburden pressure. Okay, so half into 0 plus how much here? 38, right? 0 plus 38. 0 plus 38. Okay, so this is my sigma AV into K. K I will take it as a 2. So this K value is nothing but what? Your this active earth pressure. Okay, so since you have a very very dense sand, see, even if they're not giving, if you confused with the K value, how much I should take, simply blindly you can take K value as 1. Okay, so this is always a safer side. Suppose if they given in the problem k value, then you have to take that k value. Okay, so they given in the problem k value as a 2. Okay, so 2 I am taking into tan delta. Okay, so delta value, how much delta value they given? Okay, so delta value they not given. Huh? So some researchers, what they will tell, they will ask you to take the delta value as a 2/3 or a 3/4 of your phi value, or sometimes you can even take phi itself as your delta value. Okay, so here I am taking phi itself as delta value. So my delta, I will write it here. Okay, so delta is equal to phi value according to IS 2911. So half into tan of 40 degree. How much you are getting?
31.8.
See, I'm see this surface area I'm not taking. Okay, so I'm calculating only QS for timing. Okay, so later on I will multiply this surface area. Okay, so QS I am getting how much you are getting?
31.88.
31.88. Okay, I will consider it as 32 kilonewton per meter square. Okay, so what is the important point here? How delta value? Okay, so delta value is nothing but your angle of internal friction equal to angle of internal friction. Okay, according to IS 2911. Okay, now I will calculate QSU2. Okay, that is from 2 meter to 4 meter. Okay, so half into 38 plus how much I got here? 74, no? This point 74. 74 into K into tan delta. How much you are getting?
93.9.
93.9. Okay, I will consider it as 94 kilonewton per meter square. Now another my final surface resistance, that is QSU3, that is from 4 meter to 15 meter. I think this is 6 meter, no? Yeah, this is 2 to 6 meter, and this is 6 to 15 meter. 6 to 15 meter. Okay, so so anyway here, see, from 6 to 15 meter, if you see, the variation is uniform here. Okay, so average will be 74 only. Here the variation is almost uniform. So 74 into 74 into your K value into tan delta. Tan delta is around tan 40. How much you are getting?
124.1.
124 kilonewton per meter square. Okay. Now, so what is my final QSU? That is your shaft resistance. Ultimate shaft resistance is equal to pi d. Sorry, first I will. What I will do? I will write QSU1 plus into pi dl. I should multiply with your area. Shaft resistance corresponding A will be pi into d into L. So L is first QSU and L is 2 meter only. Okay, 2 meter. So this is first term. Plus my second QSU2. Okay, so QSU2 into my surface area pi d into, yeah, what is the length of pile here? Length of pile is 2 to 6, no? That is 4 meter. Plus QSU3 into pi into D into here how what is the distance here? 6 minus 50 on 9 meter. So QSU how much you got it? 32 into 2 plus 94 into 4 plus 124 into your 9 meter into pi into what is the diameter of pile? Diameter of pile how much? 0.3. 0. So tell me how much you are getting QSU.
1406.7.
1406. 1466, huh? 1466. Is it correct? Sorry.
1406. 06.78.
1406. Okay. 1406.78 kilo Newton. Okay. So this is my shaft resistance. Okay. So now Q ultimate equal to Q base altimeter plus Q shaft altimeter. Add up all. Is there any doubts here regarding today's lecture? Snehalata,
No, sir.
are you understood the problem?
Yes, sir.
Prajwal Shetty, are you there, Prajwal? Priyadarshini,
No, sir, no doubt.
No doubt. Okay. Okay. So I will end it here. So in the next class, I will take up another problem with different layered soil. In the layered soil, you will see, and there how we can calculate the load carrying capacity of the pile. Okay. So I will stop it here.